Okay, we're going to look at free fall, which is just another type of motion that we will use kinematics for. So when we talk about free fall, it's when gravity is the only thing acting on an object. Okay. Now Galileo, scientist, and Galileo said that when we talk about free fall, we have to negate air resistance. That's why a feather falls, or sheet of paper falls slower than a crumpled sheet of paper. Everything else is the same. Just air resistance determines that it will float higher. But if there's no air resistance, all objects will have the same constant downward acceleration. So example here, sheet of paper and a rubber ball. Okay, you can see that the rubber ball drops faster because of air resistance, because the sheet of paper will have more air resistance. But if we wad up the sheet of paper and drop the ball, it'll be a lot closer to each other. So if we negate air resistance, all things will fall with the same acceleration. Free-falling objects always accelerating. They're always going to speed up as they go down, and they're always going to slow down as they go up. So for an object tossed in the air, the acceleration is the same on the way to the top as it is on the way down. And so we just want to consider acceleration to be the same for everything in free fall. So let's say we drop two rocks from rest, one after the other. When the first rock has fallen 4 meters, you drop the second rock. As the two rocks continue their free fall, does their separation increase, decrease, or stay the same? Interesting question, but let's think about this for a second. So when we look at this situation, because the first rock has already started to drop, then what we know is the first rock will always have a greater velocity than the other. And since it has a greater velocity than the other, and that velocity is always increasing, then we expect to see it constantly increase. So what we will see is that with this situation here, this rock will always increase the distance from the second rock that falls. So this rock will always be at increased distance from this one, and we'll see that distance increase throughout until it hits the water, obviously. So now free fall on Earth, we call that acceleration due to gravity g, 9.8 meters per second squared. Now, based on different locations on the Earth, that will somewhat vary, and you can see how they'll vary based on what you see here. But what we know is, 9.8 is a pretty fair number to round to. So, looking at a ball dropping, after 1 second in free fall, the velocity is increased by 9.81 meters per second, and the distance has changed 4.91 meters. After 2 seconds, our velocity just doubles. So we add 9.81 to 9.8 to our initial velocity, and we get 19.6. But look at our distance. It's now going 19.6 meters. After 3 seconds, we see this. Again, another 9.81, but our distance now is at 44 meters. And you can see this distance start to exponentially change. So distance changes exponentially, but our velocity changes 9.81 every time. Okay, boy steps off the end of a 3-meter high diving board and drops to the water below. How much time does it take for him to reach the water? What is the boy's speed on entering the water? So here's our boy jumping into the water. We know it's 3 meters high. So we know our distance, at least at the end, our x final. Our x initial be 0. Our x final would be -3 because we're going down 3. Our initial velocity will be 0. Final velocity we don't know, but our acceleration is 9.8 because we're in free fall. And since gravity's pulling us downward, that also will be negative. So we know all kinds of stuff. But we want to find position. So we look back at our equations that have position in there. And, I will go to this one. X final, X initial. We want to find final velocity. Sorry, I went way ahead of myself. So we know initial velocity, acceleration. We don't know final velocity. We don't know time. So which one doesn't have time in it? So we want to say v final squared, v initial squared, plus 2a change in x. Velocity final, we don't know. Our initial velocity is 0. 2 times our acceleration of negative 9.8. Our change in position is going to be negative 3. So in our calculator we solve, and we say 2 times negative 9.8 times negative 3 equals 58.8. We take the square root of both of these, so we take the square root of our 58, and the square root of 58 is 7.6 meters per second. So that's our final velocity. So our speed upon entering the water is 7.6 meters per second. And then how much time does it take for him to reach the water? I would go back and say VF plus VI plus AT. Final velocity 7.6. Initial velocity 0. Acceleration is negative 9.8, and we want to solve for time. And we get 7.6 divided by negative 9.8. And we get a time of negative 0.775 seconds. Now, negative time can't happen, right? How do we fix that? Well, let's look back at our problem here. When we dive down, right, our velocity final should be negative. How do we know it's negative? Because we're going down, but we don't know it's negative based on the math, but we do. Anytime we take the square root, it's always a plus-minus answer. Is it plus or minus? Well, in this case, it's going to be minus because we're going down, which makes this number negative, negative 7.6. So when we divide by negative 9.8, we do get a positive time of 0.775 seconds. Don't let the signs get you, because they will. So free fall motion is symmetrical, which is always good. And we can look at a position time graph of it. So here's our initial velocity of an object. As we start to take off, we slow down because acceleration is pulling us down until we reach this point. Now, at this point at the very top, we have no speed. We're at the very top of our motion, and there's still acceleration. We're still being pulled down with the same acceleration, but our velocity is 0. Then as our object starts to head back downward, it gains velocity. But remember, since we're going down, everything becomes negative.